Welcome to the Coherence Times, where we dive into the science and the story of quantum computing. I am your host, Ryan Mandelbaum. Every other week, I sit down with the researchers, technologists, and thought leaders to unravel the incredible challenges and breakthroughs shaping this generational technology. So, whether you are a tech enthusiast, an industry leader, or just somebody who is curious about quantum computing and how it might change the world, well, you've come to the right place. So together, I will plan on demystifying the concepts, bust the myths, and explore not just how quantum computing works, but how it can work for you. If you've listened to our first few episodes, then hopefully you're starting to get a sense of how quantum is different from today's computers and the kinds of things that we hope to do with them. Now, quantum is moving fast, but it's sort of in the same place that classical computing was back in the 1950s. Back then, we had giant machines used for running calculations and keeping track of stuff. But many of the core things that we do with computers today hadn't been invented yet. They required the creative minds of algorithm developers. So if quantum is in the same place that classical computing was in the 1950s, that means we've only scratched the surface of what these quantum computers will be capable of. And realizing those capabilities will similarly require the creativity and ingenuity and foresight of our algorithm developers. So today, I'm joined by Zaira Nazario, Director of Mathematics of Computation at IBM Research, who will tell us how we are using algorithms to chart the course for what quantum will be able to do in the future. Hello, Zaira. So thank you for joining.
Thank you for having me.
Yes, of course. So why don't you start by telling me a bit about your background and how you got into quantum?
So I'm a condensed matter theorist by training. I started my career working in quantum field theory. So I used to investigate quantum phase transitions back in the day. Also did some theory work on high temperature superconductivity. And then, life happened and life takes you places that, you don't expect. And I ended up working in the U.S. government in R&D. That's how I entered the field of quantum computing when I was asked to basically go back to my experience in superconductivity and help with a program that was dedicated to advance coherence in superconducting qubits. And eventually that path led me to quantum error correction. So when I joined IBM, I joined doing research on quantum error correction and doing research on the physics of qubits and gates. And here I am, fast forward to today.
So you've really run the gamut of quantum. Like it starts at the sort of theoretical level of just trying to figure out how this whole thing works and then actually now making quantum computers better.
Yes, pretty much. It was a very fundamental understanding the quantum mechanics of materials, quantum criticality effects and things like that. Fell in love with the renormalization group, and then from there all the way to now. How do we build these machines? How do we think about algorithms for these machines and what to do with them?
Well, that's a good segue because I would like to ask my first question, which is just what is an algorithm? And not just quantum algorithm. What's an algorithm
like in general,
all?
Right? I think it's good to start with the general, and then maybe a little bit of understanding how it works in the classical work, because usually that's the word that we're most familiar with, so it's easier to compare, if you will. So an algorithm is a set of well-defined, precise step-by-step instructions to do something, right? So you have some well-defined computational procedure with some very precise steps that takes an input, transforms it into an output to solve a well-specified computational problem in a finite amount of time. So essentially, data comes in, follows some instructions, result comes out. That's basically it. Now, you want to do that efficiently, right? So we measure efficiency usually as speed. So how long does it take to run as the size of the problem increases? But there may be other things that are important to people. Things like energy consumption. That became a pretty hot topic with AI being like this insatiable, power-hungry beast that it is. And then you also are concerned with memory requirements or communication bandwidth, things like that.
Yeah, it's a set of rules that you send to the computer, and the more efficient or the better written your rules are, then the faster the whole thing runs, right?
Exactly.
Got it. Well, how do you come up with one? I can just write one, right?
All right. How do you come up with one? Let's talk a little bit about like classical algorithms first, right? Like what is how does it work? I think like the first thing that you need is to input some data. And we do that by writing it in binary form. So be it numbers or text or images, colors, whatever it is, we write it in binary form in bit strings when we're talking about classical algorithms. Next, you need to do things with the data, right? And that's where logic operation or logic gates come into play. And we're all familiar with those, right? They're your NOT gate, which is nothing more than a flip, and your AND gate, and your OR, and your exclusive OR. So you arrange them into circuits, and those are sequences of those logic gates where time runs from left to right, and you implement those logic gates on the bits. Now, those are called Boolean circuits. Those are the building blocks for everything. Right? So now you combine those gates to build more complex Boolean circuits that you use to implement the instructions that the algorithms require you to apply on the input to get to the desired output. That could be adding or subtracting numbers, or maybe it's comparing numbers, or shifting or rotating numbers, you name it, right? But this is basically how classical computers are able to do math and conditionals and those type of things that let you perform now more complicated instructions and commands and so on.
So yeah, I think maybe it's good to just take a step back and be like, this is the basic level, the rules that we have in order to do stuff on the hardware, right? You have these bits, you have these if and or flippy things you can do to the bits, and then you'd have to convert all your math into that.
Exactly, right? Like you're playing with these like bit strings. And now, this is a podcast about quantum computing, so let me give you a way to visualize that, like, doing that, like stepping back in a way that might be familiar to your audience. Imagine that you have like some number of bits. Now, the possible combinations of the values of those bits, the zeros and ones, those are your bit streams, and they define your computational basis states. What a classical algorithm does is that it takes your input bit string and it permutes among those basis states. Now, that might be an oversimplified way, of putting it, but it gives you an intuitive way to think about it if you think about permuting those basis states in some, in some vector space. So, for example, something that shows up very frequently and like some people use sometimes as a subroutine for many other tasks is a sorting algorithm. We're all familiar with like sorting things. So imagine that you have a sequence of numbers, you want to sort them in some increasing order. Right? The input to your algorithm is the sequence of numbers that you want to solve. To sort, the output now is the sequence in the correct order. Now you have to like think about what is the set of instructions that can get me from that output from the input to the output. And a set of instructions could be, well, take adjacent numbers, say A0 and A1, compare them, then swap them if A0 is larger than A1. Right? And you can implement that comparison and the swapping instruction, all of that using these Boolean circuits. And what you're doing at the end of the day is you're permuting all of those bit strings such that the output sequence has the right order at the end.
And when you mean permuting, and so I think most folks hopefully know what a basis state and permutation is, but we should just we should get even lower just in case you don't, which is, we're flipping stuff around. You have this thing of 10, you have 10 bits, you can only be 0, 0s or 1s, so you can all these 0s and 1s, and you're moving the 0s and 1s around.
Yeah, so imagine, so one way that we find useful to visualize this one is let's say like you have only two of these objects, 2 bits. And you can visualize them in a 3-dimensional sphere that represents like, the vector space. So say that if you have 2 bits, what are the possible combinations of the values? 0, 0, 0, 1, 1, 0, 1, 1, right? And you define that. You can define it whatever you want to define it. Right? So say like I define up to be like 1, 1, down to be 0, 0, and then 0, 1, and 1, 0 are kind of like in the X and Y axis. And so when I'm talking about permuting is that you're essentially like flipping between those axes. That's essentially what you're doing there. in the
You
case
can't
of
see
the
me
two.
if you're listening, but I'm moving my hands up, down. You got a spherical thing.
90 degrees, 90 degrees, 90
1100,
degrees.
0101. You can sort of do
That's
this
right.
thing. That's
That's right. You're
permuting.
doing those rotations. Exactly.
Yeah.
Those flipping is actually like those
Yeah.
flipping. Which is different from like in the case of a quantum algorithm, right? Because in a quantum algorithm now, you also have circuits that are composed of sequence of gates or operations that you do on the qubits to manipulate the information. But now those operations, instead of giving you only those permutations, give you arbitrary rotations of the vector. So you can end up like in an intermediate sort of like, in any angle around that sphere. Right, so the point of the quantum algorithm is to give you an efficient way of implementing that rotation that you want.
Yeah, and I think folks who listened last time maybe kind of got this understanding of what zeros and ones and how classical and quantum are different. But maybe for those that don't, right, like with classical algorithms, we have just 0, 0, 1, 1, 1, etc. And then each kind of step of the algorithm is just taking that one bit string and doing a thing to it, and then just moving down the line, changing ones and zeros. But quantum, it's like you're
You're
doing
rotating,
something
right?
different. Yeah.
You're doing something different. You're implementing like these arbitrary rotations, right? It's not just permutations anymore. It's arbitrary rotations in that space. Look, like those also have to follow quantum mechanics. So what do I mean by that, right? Like, so what do those operations look like? Well, you have a well-defined quantum state. That's a vector. Think about an arrow pointing in some direction in that sphere. Exactly. Like that. And that describes the state of your quantum system, right? Now, during the computation, you're evolving that state. You're rotating it around that sphere. Now, the output in this case is something that you want to observe of the system. That could be some energy, it could be the momentum or magnetization, whatever physical quantity, right? We call those things, we call them observables. And they're described by what we call operators. Now, you can write those operators in terms of eigenvectors. Those in quantum computing, that just means the computational basis states of your computational basis states, like those vectors, if you will, that define your space and there's no overlap between them. They're orthogonal to each other. And eigenvalues. And think about eigenvalues this way. You can stretch or shrink a vector, but don't change the direction of that vector. Just stretch or shrink. Now, the eigenvalue is that factor by which you stretch or shrink the vector. And in some sense, it sort of gives you how much of the quantum state you have in the direction of the eigenvector or the basis state. Okay, so the other thing is, you don't have access to the quantum state, right? In order to know what is the state of your system, you have to measure. That measurement then projects the state of the system onto one of the eigenvectors, and the outcome that you get is the corresponding eigenvalue, right? So you get that now with a probability that is equal to the absolute value squared of the projection onto that eigenvector, right? And at that point, your quantum state basically like collapsed to a classical string with that outcome probability. So that's basically how the computation goes.
I want to make sure that we have for everybody, I understand this. I think some people understand this, but at the basic level, like we have the superposition thing, right? Where we have these bit strings. So we have, let's just work with zeros and ones. So maybe people don't get that like 0 and 1, we're kind of computing with them at the same time. That's kind of what we mean by the basis states. That
we have a
zero,
linear
zero,
combination of them.
Right, exactly. Yeah, well, yes.
Yeah.
And then if it's in a box, and this whole thing is happening in a box because you're not allowed to watch it happen because watching it happen automatically makes it not work like a quantum computer anymore. It's just a classical computer. So it's just a 0 and 1 thing. And then this whole algorithm, if this whole thing's happening in this black box, essentially you're like turning the crank and you're watching something that's kind of like probability of getting each of these output states kind of move up and down until the algorithm ends. You open the box and you're only allowed to get one of these 0, 0, 0, 1, 1, 0, or 1, 1. Does that seem like a decent understanding?
And that seems like a decent understanding. Yeah. So you're essentially like influencing. What you're trying to do is influencing the time evolution of that system, right? Like which is what gives you the rotations in that the rotations of that vector in that space. And when you're doing an algorithm, what you have to do is you have to find an efficient way of implementing those rotations, right? So influence that evolution, and at the end of the day, what is the system evolving according to? According to the Schrodinger equation with some external control parameters. So that's your playing field right there.
Schrodinger equation is the equation that just describes how it's just like the
Quantum
energy of
mechanics
something
evolved. Yeah.
Yeah, it's just how particles work. There's an equation that's just the whole thing, right?
Yeah.
Quantum algorithms sound a little different than classical algorithm. Right? A little different. So,
I would say a little different,
yeah.
yes.
And so we've got this sort of jack-in-the-box thing going on, and we're allowed to like hit the box with like our wizard hands that are doing all of these kind of quantum rotations inside of the box. So I think this answers my next question, but I'm going to ask it to you anyway, which is why can't we just run a classical computer on a classical algorithm on a quantum computer?
Right. Yes. The quantum computer does not win, like as you correctly concluded, doesn't win by doing the same things as a classical computer but faster. Right. For once, think of if you take the operations that we're implementing individually, they're orders of magnitude slower in a quantum processor than in a classical processor, right? So clock cycles in a classical processor, they take like fractions of a nanosecond. A logical cycle time in a quantum processor is on the order of a few microseconds. So, it's a lot slower. It's clearly not about running the same operations the same way. The way that the quantum computer wins is by reformulating the problem, and in doing so, changing the complexity of the problem. So that's why we need new quantum algorithms, because the game here is to change the complexity landscape of problems. And when you do that, right, some problems that are intractable or that are out of reach for classical computers from a complexity theoretic argument, now they become within reach for quantum computers. And now I can see you thinking, and some people might say, all right, so when you say complexity theory, like, what is that? Like, what do you mean by that?
Well, I do want to double click here, though, because I think this is like the most profound thing, right? Is that like people are like, oh, quantum computers are faster, but actually quantum computers are slower at doing computations. But what they can do is by changing the way you do the algorithm, you're doing things that require exponentially, hopefully, fewer steps, and that's where the real speed up happens.
That's it. Exactly. Yes.
All right.
I mean,
keep going.
Exactly. No, that's exactly what I mean when I say like from a complexity theoretic argument, right? Like complexity theory is the way that we have to understand what is and what is not computable, right? And that's important because if you can prove that something is not computable, then you don't waste your time trying to solve it exactly, right? You go and develop good approximations. Right now, all of that is based on scaling arguments, right? So you have to understand the time that it takes to run the algorithm, like how that time scales with the size of the problem or the size of the input. And so in quantum algorithms, what we try to do is, like you said, right, like is think about the problem in a different way. Can I reformulate it so I can try to bring that complexity or that scaling down from something that is super polynomial or exponential to a polynomial so that we gain as the inputs gets larger and larger.
So it's like if we're playing this game, we have these problems that we've already established take, basically as they get larger, right? If I go from trying to do it with 1, then 5, then 10, et cetera, that in the amount of time it would take increases exponentially. So, 1, 2, 4, 8, 16, 32, et cetera, that's bad. And so the idea is like, even though we have this computer that takes a little more time to do the operations, can we use those more advanced operations to do it so that it takes less time? So instead of 1, 2, 4, 8, 16, it's 1, 2, 3, 4, 5, 6, 7, 8 amount of time as the problem scales, right?
Looking at the problem with a different lens, trying to solve it in a different way, right? Like, yes.
Cool. And now, do you agree that we are sort of in this like vacuum tube era day of quantum? Like we can already do some quantum algorithms, right? Where are we at?
There are many algorithms where you can prove these scaling arguments. They tend to require, as best as we know how to implement them, they tend to require like these deep circuits where we need fault tolerance in order to achieve that. But there are some things that you can do that are variational, that are more heuristic, that you can do it by sort of like combining classical and quantum computations to be able to leverage the strengths of both for different parts of an algorithm so that we can scale better the computational capacity that we have available. And so, there's people have been developing algorithms like that and running them so they can start understanding how do they perform? Like, what type of advantages could we expect out of these things? Where could they be beneficial? If you're an industry, you have to pay attention because you want to know, how, what type of advantages could it bring me in the future, and how would they integrate with operations with the systems that I use and all of that. And those are things that take time.
So when you say heuristic, we're talking like when we go back to this complexity theory thing, 1, 2, 4, 8 versus 1, 2, 3, 4. That basically is saying that there are problems that we've proven, or at least have really strong reason to believe that they sort of have this scaling, improvement with quantum. But there's also ones where we kind of don't know, right? They're just, we got to try it out.
Yeah. In that in the case of this where you can prove how it's behaving, you have some guarantees of optimality of the algorithm, right? You're trying to analyze how it's behaving. And for those, usually you want to focus on the worst case runtime, right? How you calculate the runtime is you have to analyze how many instructions do I have to run here. That's essentially gives you how long the algorithm will run. It will depend on the size of the input, which in turn will depend on the problem that you're trying to solve. And you're trying to calculate that. It's going to be a function of the size of the problem or a function of the parameters of the system. And that function, you gave some examples. It can be an exponential of that size, or it can be a polynomial or some other function. And you focus on the worst case scenario because that gives you an upper bound. So that now you have a guarantee that no matter what the input, your algorithm is not going to run in a time worse than that. So that's why you do that. But in the case of these heuristics, you don't have those guarantees, right? So you try, you have to see how they perform. But then the tricky thing is that then in order to try to understand advantages there, you have to be very, very, very confident about the classical methods that you're comparing with, right? And you have to have confidence on those classical methods because you have to compare with the best classical that you can find, and it's a moving target all the time. But to give you some examples of what things that people are doing there, right? The general idea is that you run a limited number of large quantum systems on the quantum computer, and then you do everything else on the classical computer. So you have, one example is you can have algorithms that use quantum circuits that have some parameters, and then you get some candidate solutions using the quantum circuit, and you use classical computation to refine the parameters of that quantum circuit. So then you run another iteration with the updated parameters. You do that a few times, then to refine the solution that you get. Right. So things like there's an algorithm, the quantum approximate optimization algorithm. That's an example of that, where now the classical computation is updating the parameters of that quantum system to improve the value of the objective function. Essentially, that's what is going on there.
So this variational thing, it's like knobs, and you're turning them, and then the result is the best possible quantum solution that you then go and...
One way in which you can do that, right, is you can build some feedback loop where now the outcome of the quantum calculation, you give that as the input of a classical calculation to do more, essentially more processing, right? And so you keep iterating based on the results. You have that classical, for example, you can have a classical outer loop that does things like will prepare the input data, process the output of the quantum inner loop. Do something based on the results, and essentially that's how you do it. But in doing that, you have to keep analyzing the strengths of the quantum and the classical computations, where each can give you an advantage, and keep analyzing the trade-offs between the quantum and the classical resources.
So just kind of as we're going, you have to keep trying the best, we have to keep trying it against what the best classical thing is.
Exactly.
And hope that eventually this quantum back and forth is going to be the better way to do it.
Yes.
So this is I mean, I think this stuff is awesome. And I think the future of this, though, is not just, ideally, we're not just using these variational algorithms, these kind of back and forth quantum classical optimizing kind of algorithms, but actually trying to come up with entirely new algorithms, right?
That's right, right, and in fact, what my team is focusing on is not necessarily on these ones, right? It's on those algorithms where you can have provable separation of the quantum and the classical, where you can do those complexity theoretical scaling arguments to give you guarantees of some optimality of the algorithm. So it's a little bit different, right? And you need a lot of intuition, a lot of math intuition, physics intuition. You need a really good understanding and insights of the problem that you're trying to solve. It requires a ton of ingenuity and being able to learn lessons from failure, because you're going to try a lot of things and a lot of them are not going to work, right? And you have to be able to learn from those. But in the case of these algorithms that my team is focusing on, right, they're all rooted in the complexity of actually, in general, all the algorithms that you're going to try, they're all rooted in the complexity of problems and quantum systems, right? So you want to identify circuits that are classically hard to implement, but that are quantumly easy, right? And you need to have that intuition about what in the problem is amenable to sort of reformulate it in a way that allows you to use those circuits to evolve things quantum mechanically the way that you evolve a Schrodinger equation, such that it lowers the complexity of the problem, right? And you have to understand the symmetries in the problem and the data, because you're going to be exploiting those. You need to understand the structures, again, that you can exploit in the computation. So you have to be asking yourself things like, okay, so what makes this problem have a high complexity? Can that be mapped to a Schrodinger equation? And can I find a quantum algorithm that lets me influence the time evolution of that equation so that I can get to a solution efficiently? And then, find the most efficient way to implement those rotations that we were talking about at the beginning, right, in the evolution. And that's not an easy thing to do.
I think jankily, the thing that people might not get is that a quantum operation, right? It's essentially, not exactly, but essentially matrix multiplication. So if you add more qubits to your problem, more quantum bits, right, then it's just a ton more numbers that you're adding, because these matrices that are representing the quantum operations are getting bigger. So from my understanding then, right, a classical computer, some of those matrices can kind of be simplified in a way that makes them really easy to do math on the classical computer. But some of them might have so much mathematical messiness that in some cases the quantum computer's unique calculating abilities would be able to tackle it in a way that a classical computer can't, right?
That's right. That's right. You can have these problems that, you have all of these massive high dimensional matrices tensors, right? And it depends on the structure. For some of them, you can use classical algorithms, some randomized algorithms, for example, that let you reduce the dimensionality of the problem so you can solve it more easily. For some, you can't. So think about what is it that you're doing at the end of the day with quantum computing, right? You are exploiting these quantum mechanical phenomena like entanglement, and you are exploiting the interference of entangled states in this vast computational space, and you're doing that to process information in ways that are not possible classically, right? So I mean, again, intuitively, the fact that you have this quantum entanglement means that you have this way vaster space to encode information, right? Because in a sense, you kind of you could encode information in the spatial correlations between the states. So you have a richer way of doing computation there. But also remember that quantum mechanical states are waves. So you can you can have interference between the paths of the computation, right? You can have an amplitude of a state that is the sum of the contributions from different paths. And those contributions can interfere constructively, so you increase the probability amplitude of getting, those type of solutions. Or, they can interfere destructively to cancel out. And so, you can influence all of that, and you can influence how the system evolves through your algorithm to use those effects to get to the solution in a way that you cannot do classically. So, thinking about your analogy of when can I reduce the problem to something that I can exploit the structure to reduce it to something that I can do classically more easily versus not. So where do we expect, given all of these that we talked about entanglement and all of that, and intuitively you would think that you need problems where the answer now depend very strongly on details of exponentially many entangled degrees of freedom, right? Entangled variables or things, parameters of the problem and so on, and where there could be that structure that that quantum mechanics can exploit to evolve you to the solution. So a good guess, given the wave nature of quantum mechanics, is the structure capturing some non-trivial global properties, things like that.
Breaking it down to a couple levels, right? I think the black box with the sort of quantum crank is a good one here, because it's not like I think people think, with imagine inside this black box I've invented, it's like water. And so the height of the water, right, there's little waves going on inside of it. And so rather than it being like a black box full of jelly beans of different colors, it's more like a black box full of sloshing water. And then the location where the water is the sloshing the highest is kind of like the, labeled with a bit string, right? And then that's what you would get when you opened up the box, most likely. Right. And so but this is the thing, is that because of what's going on inside this imaginary box, this is very different than reaching your hand in and pulling out jelly beans. And you can sort of shake the box around is what your quantum operations are doing, making the waves, inside of this box act differently, or you can, hit them with different waves, something going on here. So that is how I understand the computation element of it. But I think that the part that this is, that I want to double click on as well is when we're running these algorithms, it's kind of like we have this uniquely quantum tool, like if you just have a screwdriver, and that a screwdriver is really good at unscrewing screws. And then if you go around, obviously it's not going to do useful things for most things, right? But then you arrive at a problem and you're like, oh, this thing looks just like a screw to unscrew. My quantum computer, wow, imagine that. I was creatively able to devise a whole new way to use the screwdriver. It's a lot of stuff like that, where it's just you have these mathematical tools that we know describe matter and quantum particles really well, but do these exact same mathematical tools describe some other problem, how quickly can I get to work in the morning, or how do you factor 15 into 3 and 5, right?
Yeah.
There's actually profound math connections here, right?
Yeah, so you're wondering now, what are different types of algorithms that we build with these things to solve different types of problems.
Yeah, let's do it.
And I mean, you mentioned factoring. That's probably the most famous one, right? It's Shor's algorithm to break RSA, and that gives you super polynomial speedup, and is one case where you're exploiting a very special structure that is hidden in the problem, right? Some pattern that repeats in a sequence of numbers. But you have algorithms that implement simulations of quantum systems with exponential speedup, right? You have algorithms that help you simulate time dynamics, and those are called, examples of those techniques are things like, product formula, or what people call quantum signal processing. That's just the name of the algorithm. It's a way to simulate the time dynamics of a system. And you use them to do, to understand how materials behave. For example, calculate partition functions. Those give you, again, physical quantities of a system, chemistry, physics, things like that. And then there's also, people have come up with quantum algorithms for differential equations that also should give you super polynomial speedups. There's also more recently another algorithm that uses sort of quantum Fourier transform to reduce optimization problems to decoding problems. That's supposed to give you also a super polynomial speedup. And in fact, actually, you can go to, if you want to have some fun, there's a website that is called the Quantum Algorithm Zoo, and it has lots and lots and lots and lots of quantum algorithms, right? And ways in which you can use this math to solve different types of problems.
going back, right? Partial differential. I mean, these are some of like the most important problems of our time. I think maybe it's important to harp on this a little bit, right? Like optimization is like what governs business and how it works. Like, being able to speed up optimization just helps everything. Partial differential equations is like some of the hardest things to understand in the world are like fluids moving and the air and climate, right? Which is just like a jillion variables all at the same time. And
It's also
partial
the
differential
Schrodinger equation.
equations, also just the Schrodinger equation stuff. But then there's a quantum algorithm that potentially could use quantum computers
Yeah.
to understand these systems better. This is like your climate modeling stuff, right?
Mm-hmm. To give you another example of like, something that people are familiar with, one of the things that like my team is looking at in the context of differential equation is finding efficient quantum algorithms to simulate the time dynamics of electrical networks with dissipation, right? Because those are things that are also described by a set of differential equations with some constraints, some algebraic constraints. And then yeah, I mean, there's a lot of focus on learning problems. I've mentioned several times the symmetries and the structures in problems, and we believe that things like that can happen in quantum machine learning. So there's a lot of focus there on quantum machine learning, and things like, for example, the team is working on establishing rigorous connections between some classical machine learning methods and some subroutines that you use in some of these models, and Hamiltonian simulations where we know that quantum computers excel. And so if you can find like those type of connections, perhaps there's something there that can get you some advantage.
Cool. And then there's like some pretty solid, there's definitely a lot of these algorithms that we can run today. We spoke through like the quantum, QAOA. I know there's other ones like some cool chemistry algorithms, but a lot of these algorithms, like what is it going to take to actually be able to run, to get this amazing solutions to partial differential equations running in the future?
Yeah, so more likely than not, we will need, for the ones that I'm talking about and that my team is focusing on, more likely than not, we'll need fault-tolerant quantum computers in order for the error rate in the computation to be low enough that it allows us to run circuits that are, deep enough, which are the ones that are involved here. So, this is not that far. Our roadmap has like Starling and Blue Jay coming by the end of this decade, beginning of the next decade. So, the pressure is on to find like some of these algorithms that are going to run on those machines. And then once you find them, right, like you have to work to optimize them, actually to optimize the ways that they can be implemented in that hardware, right? So because that's then another feedback loop that you have between the algorithms and the hardware that also includes like details of the choice of how you correct errors. And we make sure that, in our quantum platform in Qiskit, that we support the most promising algorithms. So, that's probably the easiest way if you're a developer to get started with this and make sure that you can take advantage of all these algorithmic advances in the future as they come.
Right. So we first need this computer that's big enough to run the problems. We've kind of established in previous episodes that quantum computing has a lot of errors that you need to then build all this redundancy in to correct. And then you have to have this algorithm not just be able to map it from kind of the textbook looking mathematics, but actually get it to run on these individual hardware units that are already running kind of redundantly in this fault tolerant regime. So then that all together is what it's going to take to run like Grover's search algorithm on a quantum computer and start doing my, Google search with my quantum computer.
That's right. That's all that it's going to take. Yes, the fault tolerance and the compilation of those algorithms into the operations and the instructions that your machine understands based on the code that you're implementing to correct errors.
And how do you get from this sort of like textbook hard math area where you're just devising cool new quantum mathematics that is faster than the best classical mathematics? And how do you kind of go about the process of then moving that over onto a quantum computer and getting people actually using them?
So that's part of what we were talking about, of like making sure that in your platform, once you have these machines that can run these algorithms and you optimize them to running hardware and do all that to make sure that you support them in your quantum platform. Because then that's essentially like the easiest way for developers to go there and use them and understand how can they be useful for the different applications that they care about. They need to understand how can they connect to the systems and the operations in their industries, in the day-to-day job, and understanding all of that takes time.
So it takes smart people who
it
are
takes
able
a combination of the people that have the knowledge to develop these quantum algorithms, working together with the people that are domain experts in the areas of the applications that are going to benefit from these algorithms, right? So because that's how you make that transition from developing the algorithms and the algorithmic building blocks to using them to enable you to solve problems that people care about.
So I think you also answered how developers can get started using these. There's Qiskit, which you are working to ensure these algorithms are implemented. All of the hard math to quantum part is done so people can just import it into their code, right? With that, I think I want to know what are you most excited about? Like, what algorithm are you just dying to see on Qiskit and then running in the world?
Well, I told you that my background is in condensed matter theory, so I'm most excited about what could we do to solve some of those condensed matter physics problems, right? So can we do what type of I'm going to use a word from the field here, but I don't know how else to describe it. But these correlation functions, and these correlation functions essentially help us describe how particles are interacting in your system, and that determines real properties of the system. It determines magnetization for example, or what is your susceptibility to something, you hit it with something, how the system is going to react. All of that you calculated using these functions. And so I'm excited about what can we learn about condensed matter physics problems by using these tools.
Yeah, I think listeners have probably recognized terms like superfluids and time crystals, and this is the field. This is cool. Answering some of these questions that always just end up in viral news articles.
Yes. Yes.
Awesome. And what do you want to see in what if quantum kind of becomes this fully grown thing that is starting to change the world? What are some places? What does a world with quantum computing look like?
It's difficult to predict this, or maybe I am not that good at predicting things. But look, I hope it's a world where we get impressive improvements in the pace at which we can innovate in certain areas. Because of course, this is not gonna be a silver bullet, right? This is not gonna solve all problems in all areas, but help us to make more improvements in how we can innovate in some areas to get answers to really hard questions. A world where in some industries are much more efficient, where science is much more efficient because we have this new tool to investigate the world. And look, hopefully a more sustainable world as well.
Well, thank you so much for coming in today, Zaira. I had so much fun talking to you about all of this. And yeah, I really appreciate it.
Thank you. Thank you, Ryan.
So that's it for this episode of the Coherence Times. If you enjoyed the conversation, please be sure to subscribe wherever you get your podcasts and share it with somebody who's curious about quantum. You can find us on Spotify, Apple Podcasts, and YouTube via the IBM Research Channel. And for more episodes, resources, and deep dives, please visit us at ibm.com/think/podcasts. I'm Ryan Mandelbaum. Thank you for tuning in. And remember, the quantum future isn't just coming, we're building it right now.